Griffiths, who is going to tell us about the invariants of normal functions. Phillip?
Thank you. I think this will be a largely expository talk on, actually, it's a fairly old subject that recently has surfaced from several different fronts, and I think it's of some interest to see what the connections might be. So the plan of the talk is first to recall some basic definitions. What is a normal function? What is a Hodge-theoretic inputs into it? And then to define the two invariants, the infinitesimal invariant, the infinitesimal invariant of a normal function, and its inhomogeneous Picard-Fuchs equation. And say a few words about the properties of these two invariants, and more importantly, what are some of the questions around them. So the underlying point is that normal functions are highly transcendental quantities. They're like period integrals, only slightly more complicated. The invariants are algebraic. They're computed from normal functions, but they're algebraic expressions. So you hope to glean some information about the normal function from these invariants. A particular issue, I think, is that the limiting behavior of families of Hodge structures is reasonably well known. It's been worked out over many years. The normal functions are particular types of mixed Hodge structures, so their limiting behavior and is in the category of mixed Hodge structures is also somewhat known. These two invariants, though, what their singular behavior is, very little is known as far as I can tell. And I think that some of the few examples indicate that this is an interesting question that really is largely unexplored. So the outline, first recalling some basic definitions, then to recall the definition of the two invariants, the infinitesimal invariant and the inhomogeneous Picard-Fuchs, and then talk a bit about the singularities of first normal functions and then the two invariants. So as I mentioned, the singularity structure of the normal function itself is pretty well understood. It's been worked out in the literature. But for the two invariants, this is not the case. Historically, the infinitesimal invariant has been used rather extensively to study algebro-geometric questions. I'll mention a few of those. The inhomogeneous Picard-Fuchs equation has been around, but it's recently surfaced in several aspects of mirror symmetry. And even more recently, both the Picard-Fuchs and the inhomogeneous Picard-Fuchs have surfaced in sort of higher normal functions, things that arise when you take the higher Chow groups. And that's of an arithmetic character. And that, the inhomogeneous Picard-Fuchs has been used for these arithmetic questions. For example, there's recently been an explanation of the irrationality of zeta 3 given by looking at Picard-Fuchs equations of particular limiting mixed Hodge structures. So for the basic definitions.
So this is Calabi-Yau's work? So whose work is this? Calabi-Yau or?
I'll mention the.
Okay.
So basic, really establishing notation. What's this? No, that doesn't work. I don't think the pointer is working here. Yeah, that's okay. A Hodge structure of weight n is given by a complex vector space and a filtration, decreasing filtration satisfying this opposite condition. And from the opposite condition, you can look to define the HPQs, FT intersect FQ, where P plus Q is equal to n minus 1. And that gives you a Hodge decomposition. So Hodge filtration satisfying the opposite condition and Hodge decomposition are equivalent. I'm always going to assume that the Hodge structure is polarized. That means it's a bilinear form, either even or symmetric or skew symmetric, depending on the parity of n. And basic example of a Hodge structure is the primitive cohomology of a smooth projective variety. Going back up to this opposite condition, when you have odd weight, 2m minus 1, then the Fm, Hodge filtration level m, plus its conjugate is isomorphic to Z. And by the polarization, this is the dual of this. So that means the definition of the intermediate Jacobian is the whole vector space modulo the first half of the Hodge filtration factored by the integral lattice. So that's a compact complex torus. In the classical case for M is where we have an algebraic curve, the first cohomology, it's the usual Jacobian variety. So these arise in algebraic geometry from the following. You take the Chow group, so those are algebraic cycles of codimension m on a variety of 2m minus 1 dimensions. You take algebraic cycles, linear combinations of irreducible subvarieties of that codimension factored by rational equivalence. Right? They sit in a one parameter family parameterized by P1. And you take something in the first half of the Hodge filtration, you look at the Chow elements in the Chow group that are trivial in homology. It's like a degree 0 divisor on a curve. That means that the cycle is topologically the boundary of some chain. And the Oval-Jacobi map then for the variety X applied to the cycle Z, it's a linear function on the first half of the Hodge filtration. It's given by integration of the form over the cycle. So that's the classical definition stacked up in dimensions. We'll also use mixed Hodge structures. That's given by a triple of a vector space, a complex vector space, a filtration defined over Q, an increasing filtration, and a Hodge filtration, such that the Hodge filtration induces a Hodge structure of weight n on the nth graded piece. So it's some filtered object whose successive quotients are pure Hodge structures. But the Hodge filtration has to come globally and be induced on these successive quotients by the weight filtration. We're going to be particularly interested in the case of a three-dimensional variety. Then the third homology of the variety modulo the support of Z. So you just take the union of the components of this cycle. A cycle is a linear combination with integer coefficients. You take simply the union of all the cycles with those coefficients made positives. Okay. So instead of a difference of 2 points, you have the sum of the points. Then that has a mixed Hodge structure that sits in the usual exact sequence. And the boundary of the chain gamma is in the second homology, it goes to 0. And I'm sorry, I've got the notation wrong. The boundary should go into Z, and it goes to 0 and X. So Z is in the kernel of this map. And so what that's saying is that this group modulo the image of homology classes is given by the kernel of the map from this to this. That's a pure Hodge structure of weight weight 1, a direct sum of Hodge structures of weight 1. So the point of this is that you have the mixed Hodge structure on X relative to Z. You have a mixed Hodge structure that's isomorphic as a mixed Hodge or the dual. Well, the height with the Tate twist to the mixed Hodge structure on the cohomology of X take out Z. And working through Poincaré Lefschetz duality, this integral I wrote of a differential form integrated over a chain, that's induced by a pairing on the tensor product of mixed Hodge structures. So that's the point of phrasing this in mixed Hodge structure language. Here I've been talking about algebraic cycles that are homologous to 0. So their fundamental class is 0. You have an oval Jacobi map on those. There's an extension of this to the Deligne cohomology, which maps any algebraic cycle of codimension M into the Deligne cohomology group. The quotient of that goes to its fundamental class. So it's the kernel of the map from Deligne cohomology to usual cohomology that are the cycles homologous to 0. Everything I'm saying can be carried over, extended to Deligne cohomology, but to keep it simple, I'll just use the traditional oval Jacobi map. Now, if we let all of this depend on parameters, you get a variation of Hodge structure. That's given by a vector bundle, Hodge filtration subbundles, a integrable connection on the vector bundle. This is the parameter space, some smooth variety, an integrable connection, and it shifts the Hodge filtration by 1. The kernel of this flat connection is the local system, and we're assuming it's defined over Z, so you have integral monogram. The cases we'll consider are the local case where you just have a polycylinder product of disks, the semi-local case, the product of punctured disks, and the global case, which is S is quasi-projective. So in the quasi-projective, in the semi-local and quasi-projective cases, you have completions. For a product of punctured disks, you just take the product of disks. For the quasi-projective variety, it has a completion where the divisor in infinity is assumed always to be a normal crossing divisor. So the typical point in the parameter space, I'll just write V in the Hodge filtration, Fp and T for the tangent space. T gives a mapping to the endomorphisms of V. Okay. It's induced from the Gauss-Menin connection, the delta, and it shifts the Hodge filtration down by 1. So it's an endomorphism of -1 relative to the Hodge filtration. The fact it's integrable means that this map induces a map of the symmetric powers of T on the endomorphisms. So the endomorphisms of V, so if you like, V is a sim T module. That's the integrability. The symmetric powers of T act on V. So to find normal functions, if you have now odd weight 2m minus 1, you get a family of complex tori, depending holomorphically on parameters. And a normal function is going to be a particular kind of section of this family. So that means that at each point you have this complex torus, and as the point varies, you have some holomorphically varied point in the family of complex tori. Right. So this is what G is, or J is as a sheaf. There's the horizontality condition, which is that if you take any lift of the map to this quotient space, lift it all the way up to a section of the bundle V, or the bundle script V, then you can take its Gauss-Menin connection, and that should only land you in Fm minus 1. So let's go back here. The normal function is the section that's it's at the bottom of the thing here. No, it's behind the top. Looks up at the top of the screen. Let me see if I can get rid of that. Okay. Whoops. Here we go. So this explains at the top what the quasi-horizontal section condition means for a normal function. It means when you lift it to a section of the whole vector bundle, the family of cohomologies, that the derivative Gauss-Menin only moves it into Fm plus 1. That's one spot next to the middle in the Hodge decomposition. And that, by the horizontality condition, is well defined independently of the lifting. So this is now not working.
Try it again.
Is that going to work now? Yeah. So this is the horizontality condition. And to prove the horizontality, what you use is that the integral of differential forms over cycles is really a pairing between the tensor product of mixed Hodge structures. If you apply a Gauss-Menin to the tensor product, then you apply it in the usual way, the Leibniz formula, and use the transversality on each factor, and that translates into this horizontality condition. Okay, so this is just the argument that that in the geometric case, this horizontality constraint on a normal function is well defined. Particular case of interest is when, instead of looking at the integral of a differential form in the first half of the Hodge filtration, you only look at the integral for the first piece, the purely holomorphic piece. Okay. And that's going to be called a truncated normal function. Those are the ones I'll mainly use later on when they restrict to Calabi-Yau threefolds. So this is the definition then, the truncated normal function. You just consider the integral of the first piece, where the differential forms come out of the first piece in the Hodge decomposition. So in the Calabi-Yau threefold case, then we're always going to take, for the parameter space, the full moduli, local moduli space is unobstructed by the classical BTT theorem. And then you have an isomorphism where you apply a tangent vector to the first piece in the Hodge decomposition, you get the isomorphic to the second piece. So when you differentiate these integrals just using the first piece, because of this, you get the derivative of everything in the first half of the Hodge decomposition. So you don't lose any information in this case by looking at these truncated normal functions. So this just elaborates on what I said. If you have a family of Calabi-Yau, in the geometric case, a family of Calabi-Yau threefolds, then the tangent space to the parameter space is the second summand in the Hodge decomposition. The first summand, when you apply tangent vectors, goes isomorphically to the second piece in the Hodge summand. There's a very nice construction from this. If you count dimensions, the number of moduli is one less than the dimension of the intermediate Jacobian. Okay, the number of moduli is the dimension of the second piece in the Hodge decomposition. The dimension of the intermediate Jacobian is 1 for the n piece plus the dimension of the second piece. There's a construction that goes back to the Lagrangian and Markham that you look at the pullback of, well, you take the C star bundle over moduli corresponding to just the line bundle is the first piece in the Hodge decomposition. Pull back the family of intermediate Jacobians, and that gives you then a family of compact complex tori over a base space of the same dimension. Okay, so it has even dimension. And the Donaghy-Markman theorem is that this is a symplectic manifold, and the graphs of normal functions are Lagrangian submanifolds. So geometrically what's going on is this, that if you take a family of algebraic, so this is in the threefold case, take a family of algebraic one cycles that in every, that maps dominantly onto the parameter space for the family of Calabi-Yaus. So every one of the Calabi-Yaus will have a bunch of one cycles in it, okay? And pull back, then that, so that's this family of one cycles mapping to the total space, we'll call R the parameter space. So it's a family of algebraic one cycles on these Calabi-Yaus, pull it back to this line bundle over the moduli space, and that gives you a natural normal function. So since I'm assuming this family maps dominantly down to moduli, the graph of this normal function is something of half the dimension of the total space. I said that the total space is a symplectic manifold, and the Donaghy-Markman theorem is that the graph of the normal function is Lagrangian. So the proof of this theorem uses this Yukawa cubic, which is ubiquitous in this whole business. The Yukawa cubic is something in the third symmetric power of the cotangent space to moduli with a scaling factor, the first piece in the Hodge decomposition squared. Well, it's the last piece squared. And going back to what I said, that the symmetric powers of T act on the vector space V, the cohomology, shifting the Hodge decomposition by 1 for each vector in T. And it's just this picture here. So if you iterate this 3 times, you end up with a cubic. And that's the you call a cubic defined at the scale. We'll see that reappear later in several guises.
So this is just something that you call with Brian cubic condition related to this particular case.
Yes. So for the invariant of normal function, first the infinitesimal invariant, given a variation of Hodge structure of weight 2m minus 1, a normal function, the infinitesimal invariant is going to be a section of a family of Kazoo cohomology groups. Okay. So it's a section of a vector bundle, but the vector bundle are not directly constructed from the Hodge structure. They're constructed from Kazoo cohomology arising from the induced mappings from the Gauss-Menin connection on the family of Hodge structures. Specifically, the Gauss-Menin connection induces, by dualizing it, this short exact sequence. This is the dual of the tangent space to the parameter space. And this is a complex, it's a Kazoo complex. And the infinitesimal invariant is gotten as follows. You take a local lift of the normal function to a section of V, take its Gauss-Menin connection, that's an Fm minus 1, delta squared equals 0 gives you the section of this kernel. It's defined modulo this thing, modulo the image of Gauss-Menin coming 1 step down. The infinitesimal invariant is then the section of the middle cohomology groups in the Kazoo complex. Okay. So what you're doing is simply taking the Gauss-Menin delta squared is 0. That suggests cohomology. However, the normal function is a section of some quotients. So you lift to the total space, take Gauss-Menin, it gives you a cycle, and the ambiguity you have to factor out. That puts you into the Kazoo cohomology group. So that's the infinitesimal invariant. If it's 0, that means that the normal function lifts to a constant section of the cohomology bundle. Okay. Doesn't mean the normal function is 0, just means it lifts to a constant section. In certain global cases, you can use a monodromy argument to show that if it lifts to a constant section, it must be torsion. So even though it's doesn't capture the normal function, in a lot of cases in geometry, it captures it up to torsion. So a standard example is if you take R, this parameter space of curves in a Calabi-Yau, and you take the normal function gotten by taking just the difference of 2 curves in the same homology class, then it's known that generically this infinitesimal invariant is non-zero. I don't know the original argument, but it appears sort of scattered in the literature. This is for, I'm sorry, let's see, space. I'm sorry, this is for the quintic. And the rational curves you take are the lines on the quintic. So that's the case that you know that generically this infinitesimal invariant is non-zero. The open question, as far as I know, is if you take any Calabi-Yau, not just the quintic, but any Calabi-Yau, take rational curves, not just lines on the quintic, but any rational curves on Calabi-Yaus, is the same result holds, that generically this infinitesimal invariant is non-zero. That's maybe related to the Clemens conjecture that says that on a generic Calabi-Yau, any rational curve is locally rigid. The normal bundle is O of minus 1 plus O of minus 1. This infinitesimal invariant has a lot of uses in algebraic geometry over the years. One of the first ones was that Clemens and Lausanne proved that for generic Calabi-Yau, the image of algebraic one cycles, just take all of them, not just rational curves, but take anything, that the image is a countably infinite discrete group that's not finitely generated, unless it's infinitely generated. So it's a mysterious object because it's discrete, it's a group, but it's not finitely generated. A second use of this infinitesimal invariant turned up in the early 80s, the Teresa cycle. You take an algebraic curve and take the Jacobian variety, that's an abelian variety of the algebraic curve. The curve maps into its Jacobian by the Abel-Jacobi map. So for the Jacobian of a curve, you have a curve of one cycle sitting in it. Take that one cycle minus the minus on the group structure on the Jacobian variety. So that's one curve minus a curve that's in the same homology class, but it's a different curve. And that's the Teresa cycle. And the theorem proved over the years is that generically the infinitesimal invariant is non-zero, and from that one concludes that this cycle is homologous to zero, but not algebraically equivalent to zero. It's a very concrete object that has this interesting geometric property. Another example discussed earlier was a smooth cubic threefold with final surface of lines on it. There's a recent paper by Colino Mariano and Corolla that shows how you can reconstruct the cubic threefold from this infinitesimal invariant, where the normal function is the difference of the final surface mapped into the intermediate Jacobian. Do the same thing as with the Teresa cycle, just take minus it. That gives you an algebraic 2 cycle in this 5-dimensional abelian variety, and the delta nu of that, when you vary the cubic threefold, you can reconstruct the cubic threefold from that.
This is different proof of Turel. A different proof of Turel.
Yes. Okay. Finally, for a family of Calabi-Yau threefolds, where you use the local moduli space, then the Yukawa cubic that I mentioned a little while ago, the infinitesimal invariant is constructed from the Yukawa cubic. It's the second symmetric power of the cotangent space modulo the Jacobian ideal of the cubic. That is, in this case, the first partials of this cubic gives you a bunch of quadrics. You mod those out from all the quadrics, and that's where this delta nu sits. So there it is at the top of this slide. And there are probably specific computations of what this delta nu is. You take a particular your favorite Calabi-Yau threefold, the Fermat or whatever, it can be computed. I've not seen that done, but what it does show is, again, this Yukawa cubic, which I think to the mathematical physicists is this obvious, keeps turning up all over the place in various guises. And here it turns up in the delta nu. An interesting question that I've not seen discussed, it may be in the literature, I don't know if it is, no, but how does the cubic vary with the Calabi-Yau? So the variation of the cubic is a map from the tangent space to cubic polynomials. You have to factor out the Jacobian ideal to make it well defined. So that's what the variation of the Euclid cubic, that's how you measure it. Or if you like, it's some object in this tensor product. So again, there's a Cazul complex, sort of the obvious one from this algebraic situation, and the psi sits here in the middle. It can be computed that it goes to 0 here, so it gives you an element in the Cazul homology. So the definition, if you like, of the variation of the Euclid cubic is the homology class constructed just before. And I've not seen this in the literature or any examples of it, but it's a natural object to think about. So turning to the inhomogeneous Picard-Fuchs equation, I'm going to restrict to the case of Calabi-Yau threefolds here. So we take a family of Calabi-Yau threefolds, and I'll use this round D to be the just a one parameter family for the moment. I'll use round D to be the Gaussian applied to ddt, and assume that the derivatives of the holomorphic differential, you choose a holomorphic differential, non-zero at each point, and just differentiate it. Assume that those derivatives generate all the cohomology. That's usually the case, or frequently the case, and you can always reduce to this situation. So assume that. Then there's a unique equation. If the dimension of the cohomology is R, there's a unique equation when satisfied by the derivatives of omega. This is 0 in the cohomology. That's the Picard-Fuchs equation. Okay. So there it is written out. For example, again, for the Euclid cubic, if you take the quintic, the Picard-Fuchs is just this equation written here, where the Euclid cubics in the denominator. You have to make sense out of what this quotient means, or that requires a little interpretation, but I'm not going to do that. The notation suggests what the character of the thing that you're going to get for the Picard-Fuchs equation. So we're going to use this truncated normal function where you just integrate the holomorphic differential, not the whole first half of the Hodge decomposition, just the first piece. Okay, and that'll give you some truncated normal function. For simplicity, I'm just going to look at algebraic cycles that are the difference of irreducible ones. We have a mixed Hodge structure on the variety minus the sum of these. That's just an ordinary curve, reducible curve on a threefold. You have this exact sequence of mixed Hodge structures. The cohomology of X restricts to or maps to the cohomology, the relative cohomology, and I think I wanted here, yes, it maps to the cohomology of the complement, and the boundary or the residue takes you to Q of minus 1. Okay, so that's the exact sequence for the mixed Hodge structures on the complement of the support of this cycle. The weight 3 part is the cohomology of the Calabi-Yau, and the quotient has weight 4 is just a Q of minus, it should be a Q of minus 2, I guess. The inhomogeneous Picard-Fuchs equation is just apply the Picard-Fuchs operator P to the normal function, okay, and call that f. So f is a function. Recall that the normal function is defined up to adding periods. The Picard-Fuchs equation annihilates periods, integrals of omega over any topological integral cycle. So it's well-defined function. It does depend on, usually when you map to a Jacobian variety, you have to factor by mapping to a vector space modulo a lattice. You have to factor out the lattice. That's annihilated by the Picard-Fuchs equation. That gives you the inhomogeneous Picard-Fuchs equation. Okay. So this has been considered in the physics literature a number of places. For example, there's a paper by Morrison and Walter where they look at the quintic, and on the quintic they look at the difference of a pair of lines on quintics. And I'll come back to that equation in a little while. Another example that was considered by Golechev and Kerr of these higher normal functions, and this is a reference to a paper of Kerr, Lewis, and Mueller-Stock. The higher normal functions map the higher Chow groups. N equals 0 is the usual Chow group. This is the usual auto-Jacobi mapping. N equals 1, N equals 2, and so on, are the higher Chow groups, which have arithmetic meaning. I'll illustrate that in just a minute. And those map to some object that's like the intermediate Jacobian. So this is the map. Higher Chow group goes to a generalized intermediate Jacobian. And this is what it is. It's the cohomology but complex coefficients modulo fp plus f, the cohomology 2p minus n. Because that's you're looking at codimension p, but you take the cohomology in dimension 2p minus n. Only when n equals 0 is it the usual thing. So that's the definition of this, and one can define these higher auto-Jacobi maps. For n equals 0, it's the classical case, and for n positive, what you get are what are called mobile regulators, and I'll give an illustration of what those look like in an example. Again, from Calabi-Yau. So the point here is that normal functions exist not just for classical mapping algebraic cycles to a compact complex torus, but they exist for these higher Chow groups mapping to a complex manifold. It's no longer a compact complex torus, but it is a complex manifold. It's a complex Lie group factored by a discrete abelian subgroup. An observation is that the inhomogeneous Picard-Fuchs equation, the right-hand side satisfies a linear first-order equation. Okay. So you could write it this way using the previous notation. Why is that? Well, you think of the structure of the Gauss-Menin connection in this sequence here. Okay. We know what it looks like on the first part, the Gauss-Menin. Here it's sort of easy. That's basically a constant family of Hodge structures. So you can deduce what the Gauss-Menin looks like here. And if the Gauss-Menin annihilates this, you end up with just linear first-order equation. So that's the sort of geometric explanation of why the inhomogeneous, the right-hand side of the inhomogeneous Picard-Fuchs satisfies a linear first-order differential equation. If you have several parameters, you use D modules and all of this. The essential story, so far as I can tell, is pretty much captured by the one parameter case. So by way of comparison of these invariants, the infinitesimal invariant is first order, and it's constant only if you have a constant lift. The inhomogeneous Picard-Fuchs, well, the Picard-Fuchs is of mu is 0 of a normal function if and only if it's torsion. So that's much stronger. The reason that you get that is Picard-Fuchs equals 0 means that the mu is a linear combination of complex periods, C coefficients. But this cohomology of Q tensor C is the third cohomology C with complex coefficients. For this reason, annihilating a linear combination here with complex constant C coefficients is equivalent to annihilating a linear combination with rational coefficients. That means the torsions, that the normal function is torsion. Just a couple of further remarks in just to give somewhat the flavor of this infinitesimal invariant. For algebraic curves, so we understand the local moduli of algebraic curves. The tangent base is the first cohomology of the tangent sheaf, which is dual to the zeroth cohomology of the square of the canonical bundle, quadratic differentials. Okay. You can look at, so what does that mean geometrically? That means that the algebraic, except in the hyperelliptic case, the algebraic curve is the bicanonical model is sitting in the projective space associated to the tangent space to moduli. So the point here is that you could look at the rank 1 deformation. So rank 1 just means that it's a linear map between two vector spaces, and rank 1 is just means rank 1. You could ask, what are the rank 1 deformations for algebraic curve? You have the bicanonical curve sitting in the tangent space to the parameter space, tangent space to moduli. The rank 1 deformations are just the points on the bicanonical curve, the so-called Schiffer variation. The way to think of that is you have a complex Riemann surface, you have a point, the complex structure changes by a delta function. Delta function is 0 outside the point, and it's a delta function at the point. These are the Schiffer variations. So what I've shown here is that the differential of the variation of the period matrix reconstructs the algebraic curve by locating its bicanonical model as the rank 1 elements in the differential. So that's essentially the reconstruction of the non-hyperelliptic curve from its infinitesimal invariant. For the cubic threefold, there are no rank 1, for the moduli of the cubic threefold, there are no rank 1 transformations, but there are transformations of rank 2. The paper I mentioned earlier reconstructs the fauna surface from the rank 2 deformations using this infinitesimal invariant. So the point is that from this infinitesimal invariant, in some cases, you can use geometric arguments to dig out interesting information, for example, the original variety itself. That brings up, of course, the question for a Calabi-Yau threefold and a family of rational curves. Can you generically determine the threefold and the pair of curves from the infinitesimal invariant? Is there a sort of Torelli phenomenon that's captured by this infinitesimal invariant? I think I will skip this. I'm running out of time. I want to say just a few words about the singularities. So if you have either the quasi-local, semi-local case, punctured polycylinder completed to a polycylinder, or the global case, a quasi-projective variety completed to a complete projective variety, there, how you want to define the extension nu bar of a normal function, delta nu bar of its delta infinitesimal invariant, and of the Picard-Fuchs equation, the inhomogeneous one, and to understand what their singularities are along the divisor at infinity. Okay. That's, I think, in my mind, one of the big open questions in this business. So, for example, this is only what is understood is what nu bar is. So it was worked out about 20 years ago, just how you complete the family of intermediate Jacobians first in one parameter and then in general, and extend the normal function to the completion. I'll just call that nu bar. So for normal functions, it's understood what happens when you complete. What about these invariants? For the inhomogeneous Picard-Fuchs, in the one-dimensional case, the singularities are understood, and I'll explain what those are in just a minute. Going to restrict to the geometric case, these completions are done in general, but let's just do the geometric case. And you look at a family of cycles in a completed variety, whose intersections of the fibers are proper, and you have various things to consider. Is there a well-defined oval Jacobi map on the singular variety itself? Or secondly, is there a limit from the oval Jacobi maps on the smooth fiber as you've approached the origin? So those are two basic questions about behavior of oval Jacobi map. There are various cases to consider. One is that the fundamental class of the cycle is zero when you take out the singular fiber. The second is that zero when you complete the whole thing. And the third is that the restriction to each fiber is zero in cohomology. So the relation between these is well understood. It's the Clement-Schmidt exact sequence, basically. And the first two steps about what those two objects are is also well understood. What is not understood is what happens to their invariants, the delta nu and the Picard-Fuchs. For the references, I just gave one here. This whole story is, there's an expository article that pretty much is a good accounting of the whole business, and that's the reference. Paper by Matt Kerr and Greg Perlstein. So going back to the singularity of Picard-Fuchs, where right-hand side is just a function on, when you're looking at near the singularity, one uses the logarithmic form of differentiation, call that theta z ddz over is equal to dt, and write the equation as p plus these are functions here. One knows that the Picard-Fuchs has a regular singular point, so these are analytic functions. So the Gauss-Menin for the variation of mixed Hodge structure given by the cohomology of the variety minus the support of these subvarieties, that's a linear first order equation. It has a regular singular point, so you can always put it in normal form, just one differentiation plus a constant. And because it's a regular singular point, the real part of the constant is non-negative. Because of monodromy, the constant is a positive or non-negative rational number. So what that boils down to is the singularity of the inhomogeneous Picard-Fuchs equation in one parameter is well understood. And that's what the solution looks like, lambda's non-negative rational number. For example, the Morrison-Walcher example of the Fermat, where you take a pair of lines, they compute it out to be just the square root of z, where the square root just is the monodromy. When you take a pair of lines on order around the origin, the order reverses. So that's the reason for the square root. So to close, let's go to the semi-local case in odd dimensions, and where the limit of the Hodge structures as a limiting mixed Hodge structure is known. It's constructed from monodromy. The weight filtration is defined by the monodromy we can assume to be unipotent. So this is a nilpotent matrix, and one can use that to define the weight filtration. The limiting Hodge filtration is also defined not exactly only up to scaling by the exponential of the one parameter group generated by the log of monodromy. So one has a good picture of what happens to the Hodge structures. A naive way to fill in the family of intermediate Jacobians would be just do the same thing that you did at a smooth point. And this works classically for curves, and it works in general when n squared is 0, like an ordinary double point. That would be an example. But it doesn't work otherwise. Okay? You have to do something non-classical. And that eventually, that can be worked out. What you fill in over the origin is the intermediate Jacobian not constructed from the full cohomology, but only on the kernel of the logarithm of monodromy. It's a very non-classical object. The total space is what's called a slit analytic space. It arose in this work of Kato Usui. It's something you can do geometry on. It's not necessarily a very pretty object, but somehow it works. In the one parameter case, I'm going to run out of time.
It's okay, it's okay.
Huh?
We just that.
In the one parameter case, the normal function always extends to give you something which is a Neron model. It's an extension of a compact complex torus by a finite group. This is the finite group here. Okay. The fact that it's a finite group is a non-trivial result. It's called the local invariant cycle theorem. In any case, in one parameter, the normal function itself, after you multiply it, always extends to give you something in a complex analytic Lie group over the origin. We'll call that mu sub e. What is that object? Well, when you work it out, the way you get it is that you look at the normal crossing divisor sitting over the origin. It has a stratification. The highest dimensional strata are just the components of the same dimension as the smooth fiber. Then you have double codimension 1, double locus, codimension 2, triple locus, and so on. Okay. When you go down to codimension n, you end up in the limit of the oval Jacobi map, looking at the oval Jacobi map on these higher Chow groups, where the n in the higher Chow groups is the codimension. So even if you didn't start out being interested in arithmetic things, they end up in your lap at the origin. So, for example, I'll just conclude with two examples. I should remark, by the way, that in some of the physics literature, which I think probably less familiar with than any of you, but I've seen mention and the question raised, okay, in mirror symmetry, we're interested in these inhomogeneous Picard-Fuchs equations and normal functions and their limits. In the limit, we get this thing that's arithmetic. It depends on fields of definition of things. What in the world does that have to do with mirror symmetry? So, I mean, maybe. So, coming to the final example, for Calabi-Yau threefold, we have the usual Jacobi on the highest dimensional components over the origin. Go down to the next components, the double loci. To give you the geometric flavor, what you have on these double intersections is a surface, usually a K3, and the limit of your algebraic cycles will give you something in K1 of this K3, in the sense of K-theory. Or K2, I guess it is. Specifically, that's given on this surface by a bunch of algebraic curves, and on each curve you have a meromorphic function, and the zeros and poles cancel out. So on one component, the zero is equal to the infinite component of the function on the other cycle. So what that gives you is then a cycle of degree 0 on the union of these curves. On each curve, you have a cycle of degree 0. So there's a one chain whose boundary is on each individual curve. That's because the zeros and poles cancel out, right? Those points are homologous on an irreducible curve. So what that gives you is something in H1 of this reducible curve. Okay. And from the formalism, this H1 on the irreducible curve bounds in the ambient surface. So it bounds a two-chain. The limit of the holomorphic differential on the Calabi-Yau threefold will acquire poles on this double surface. So you take their residues, those give you holomorphic two forms on this surface. You have a two-chain, and you integrate that holomorphic two form over that two-chain. That's what these limits of Jacobi maps, the sort of flavor of them. So closing for the codimension 3 locus, this is in the curve Perlstein paper. With this pencil, standard pencil of Quintix, what it's proved is that the oval Jacobi map of the limit of the singular fiber contains the indecomposable elements in K3 of C. That's coming off of the codimension 2 locus. And the oval Jacobi map is the regulator map from K3 to C mod 2 pi IQ raised to some power. Well, in this case, just first power. And the regulator just maps that to R. That's the usual number theoretic object. So that's the flavor of what the limit of these oval Jacobi maps look like when you get into the higher codimension strata. They have a very arithmetic character. If you go changing the field of definition, conjugating under Galois groups and so on, these things bounce around. So to conclude, the conclusion was really, I was going to give some more example, but I think at this stage I'll just stop. I think the main takeaway is that there are these interesting invariants of normal functions They've been quite useful in some classical questions. What is not understood is what they look like in the limit, and what information, geometric, physical, number theoretic, might be lurking in what the limits of these two invariants might be. Thank you.
Where is it?